Greetings, Doctor. My name is Kyung Wei Ming. My metric number is TH24080. Before we begin, I would like to introduce my group members. Our group consists of Kuhan anak lelaki Wejendram with metric number TH24002. Next, Suman anak lelaki M. Selvam with metric number TH24009. Next, Kishan anak lelaki S. Ramachandran with metric number TH24039. For last is Muhammad Dennis Haziq bin Muhammad Nasri with metric number TH24050. Today, we will be present our project title is Lifting Oil with a Pump under concept System of Particle, Work and Energy. This project focus on analyze how a pump transfers crude oil from a lower tank to a higher storage tank by applying the engineering dynamics concept of System of Particle under Work and Energy. First, executive summary. Our project focus on a booster pump system used to transfer crude oil from a lower tank to a higher storage tank in petroleum operations. For this project, we apply the engineering dynamic concept of system of particle, specifically under the topic of work and energy. The crude oil flowing in the pipeline was analyzed as a system of particle, where energy from the pump is transferred to move the fluid and overcome gravity. From our analysis, we calculated the minimum pump work required 157.65 joule per kilogram and the pump power required 15.81 kilowatt. The results show that as the elevation difference increase, more pump power is needed. Therefore, proper pump selection and efficient system design are important to reduce energy consumption and improve petroleum transportation efficiency. Moving on to the introduction, in the petroleum industry, crude oil is commonly transported through pipeline system for storage and processing operations. In many cases, the oil needs to be transferred from a lower storage tank to a higher storage tank. To make this process possible, a booster pump is used to provide the mechanical energy needed to move the fluid continuously and overcome gravity caused by the elevation difference. An efficient pumping system is very important because it helps maintain continuous operation while reducing unnecessary energy consumption and operating costs. However, one of the main engineering challenges is determining how much energy the pump must provide to transfer crude oil efficiently. If the pump supplies insufficient energy, the flow rate may decrease and affect system performance. On the other hand, excessive pump power can increase energy consumption and operating costs. Therefore, this project focuses on analyze how velocity change and elevation difference affect the pump work and power required for crude oil transportation. Next, objective. The objective of this project are to analyze the crude oil pumping system by applying the engineering dynamic concept of system of particle under work and energy. First, our objective is to model the crude oil flow in the pipeline as a system of particle and study how energy is transferred during the pumping process. Second, we aim to determine the change in kinetic energy and potential energy of the crude oil as it's moved from the lower tank to the higher storage tank. Next, we calculate the minimum pump work and pump power required under the given operating condition. Lastly, we analyze how different elevation height affect a pump performance and provide recommendation to improve energy efficiency in petroleum transportation system.
Assalamualaikum, good afternoon. My name is Muhammad Danish Haziq bin Muhammad Nasri with matrix number TH24050. Move to the next part, which is the system description. The fluid transfer system is designed to transport oil from a low elevation reservoir to a higher elevation storage facility. The system configuration is defined by the following primary components. At first, we have the lower collection tank. As we know, as a reservoir, it acts as the suction source for the system, maintained at a static pressure and elevation which is known as Z1. It also provides a constant supply of fluid to the pump inlet. Second, we have the booster pump. Booster pump is served as the prime mover, converting mechanical energy into hydraulic energy to overcome the elevation head and provide the necessary pressure to transport the oil to the discharge point. Third, we have the pipeline network. Pipeline network consists of the conduit system connecting the pump discharge to the destination. It serves as the physical path for the fluid transport. At last, we have the higher storage tank, which the destination located at a higher elevation, known as Z2, where the fluid is collected. As we can see here in the diagram here, the flow direction is from the lower tank to the pump, to the pipeline, and lastly to the storage tank. To facilitate the theoretical analysis and baseline performance calculation for the centrifugal pump training model, the following assumption have been applied. First, we have the steady state flow. So basically, the mass flow rate and the fluid properties at any given point in the system do not vary with time. So this allows for the use of the Bernoulli equation without temporal derivative terms. Second, we have the incompressible fluid. The oil is treated as a Newtonian fluid with constant density. As the pressure variation in this system are not extreme, so density changes are not the density changes are considered negligible. Third, we have the negligible friction losses. Major losses due to pipe wall roughness and minor losses due to fittings, elbows, and valve are excluded from the initial energy balance to establish the theoretical ideal power requirements. Fourth, we have uniform velocity distribution. The velocity profile across the cross section of the pipe is assumed to be uniform, which known as a plug flow, allowing for the use of average velocity in the kinetic energy terms of the energy equation. At fifth, we have the ideal pump efficiency. The pump is assumed to have an efficiency of 100%. This implies that all mechanical energy supplied by the pump is transferred directly to the fluid without internal losses, such as a mechanical friction or hydraulic recirculation. At last, we have no energy losses. Aside from friction, all other potential energy dissipation, including those from transition, turbulence, or control valves, are neglected to isolate the effect of static head on the system requirements.
Hi, my name is Konrad Ujindran. My matrix number is TH24002. And for the theory equation part, I'm going to explain about the certain formulas that we use to conduct our calculation methodology. So for first, I'm going to start with our work energy principle, which is the work energy principle asserts that the work done on a system is equal to the change in the total mechanical energy of the system. This energy is supplied by the pump is transformed into the various of kinetic and potential energy of the crude oil as it flows from the pump outlet to the inlet of storage tank in the pumping system considered in this work. So the general equation of this work is the U equal to total kinetic energy plus total change in potential energy, while the U1 to 2 is considered work done by pump, and KE consider change in kinetic energy, and PE consider potential energy. And now for the change in kinetic energy formula, which is KE equal to V2 square minus V1 square over 2, which the V1 is considered velocity of crude oil at the pump outlet, unit M over S, and for the V2 consider velocity of crude oil at the storage tank inlet, unit is the meter per second. And this velocity of the crude oil in pipeline may be different at the pump exit and at the storage tank intake, while the kinetic energy changes in proportion to any change in velocity. So the kinetic energy is the per unit mass of fluid. And for the second is the change in potential energy. So formula for the potential energy, which is PE is equal to G in brackets G2 minus G1. The G considered as a gravitational acceleration 9.81 meter per second square,
G square consider the elevation at the pump outlet meter. Z1 is considered elevation at the storage tank inlet unit is the meter. And this formula is considered when crude oil is moved from a lower to higher elevation, while the gravitational potential energy of the crude oil is increases through the pump outlet. And now for the minimum pump work required formula, which is WP is equal to change in kinetic energy and change in potential energy, which we discussed earlier in the previous slide. So the formula is in terms of can be summed to obtain the minimum power work per unit mass of crude oil. This equation demonstrates that the total work supplied by the pump is made up of two different parts. The first part is the energy to speed up the fluid, and second part which is energy needed to lift the fluid to a greater height. And also this equation heat transport effects and frictional losses. Thus the computative value is the theoretical minimum work that must be supplied by the pump. And for the last formula we are going to discuss about is the pump work required, which is P equal mass flow rate times minimum work required by the pump. And for the mass flow rate, M formula is considered mass flow rate of crude oil with the unit kilogram per second, and the unit for WP is the J per kilogram. And this work of pump formula is the measure of the energy required per unit of mass of fluid. Since the pump run continuously and consume electrical energy, engineers are primarily concerned with the power requirement. So therefore, to drive a pump depends on the energy per kilogram of fluid and the rate of fluid carried in the kilogram per second. So while the power usage is related to the flow rate, similarly the larger elevation difference between the tank means more pumping level and also more power is needed due to the general consideration. And now move on to the methodology part. The purpose of this current analysis is to find out the minimum level required by the booster pump to transfer crude oil from lower collection tank to a higher storage tank. So for the conducting the further explanation for the calculation part, we are going to do a flow chart of the work, which start from define the physical property of system and operating settings, and followed by determine bulk flow rate of the crude oil, and followed by change of kinetic fluid energy and to the potential energy shift from change in elevation. And both from the kinetic and the potential energy, we are going to find the minimal work of the pump per unit mass. And for the minimal work of the pump, we are going to determine the necessary power to efficiently work the pump to maintain the desired flow rate. And while all this is done, lastly we will examine the effect of elevation difference on pump performance as the general equation. And now for the operating data for our calculation part. So for analysis, industrial values were assumed. The values are deemed reasonable for crude oil transportation system functioning within the petroleum storage facilities. And these parameters are such as oil density, simple, rho, value is 850 kg per meter cube. Second, volumetric flow rate, symbolized as Q, value 0.118 meter cube per second. And third one is elevation difference, symbolizing as Z, the value is 15 meter. The Z is the difference between the upper level and the lower level. And for fourth one is inlet velocity, V1 as symbol, and value is 2 meter per second. And for the outlet velocity, which is V2 symbol, and the value is 5 meter per second. And for lastly is the gravitational acceleration, which is symbolized as the G alphabet. For a value, we consider 9.81 meter per second square. And now continue the calculation part. We start from mass flow rate calculation, and this mass flow calculation is the quantity of crude oil flowing through the pipeline in specified period. And for computing this equation, we're going to use the M equal to PQ, rho Q is equal to 850 times 0.5. We got a 100.3 kilogram per second mass flow rate of the crude oil. And for next one is the calculation of change in kinetic energy. So as we substitute the values of V square and V1 into the formula, we are going to get the 10.5 joule per kilogram. This change in velocity results in the change in kinetic energy. Therefore, the kinetic energy of the crude oil is 10.5 J per kilogram, which is a relatively small value obtained indicates that only a modest amount of energy is required to increase the fluid velocity within the system. And furthermore, to the change in potential energy calculation, as we substitute the value of gravitational energy and different elevation into the formula, we are going to get the 147.15 J per kilogram, which is the crude oil is pumped from the lower collection tank to a storage tank located 15 meter above the reference level. Therefore, the potential energy of the crude oil is 147.15 joule per kilogram, which shows the majority of the energy supplied by the pump is used to overcome the elevation difference between two tanks. And therefore we're going to the minimum pump work required calculation. We're going to substitute both the change in kinetic energy and the change in potential energy somehow into the formula. So we're gonna get 157.65 joule per kilogram amount. So this work energy principle states the minimum work that a pump should be equal to the sum of changes in kinetic and potential energies, which the minimum power required to transfer crude oil is 157.65 joule per kilogram, which represents the theoretical minimum energy requirement under ideal conditions where friction losses are neglected. And now for the calculation of pump work power required, which is as we substitute the mass flow rate value and the minimum work and minimum work by the pump as we calculated as before. So I just substitute into the formula, we're gonna get the 15,812.30 work. Therefore, the pump required by the pump to power the transport crude oil is 15,812.30 work at the specific operating condition. And as we got all the calculation from the previous power to pump the crude oil, now we are going to calculate the effect of different elevation on pump power required, which is why we are going to conduct the values on the different elevations such as 35 meter, 35 meter, 45 meter, and 55 meter. And the table here represents the value that we have got from the substitute the value into the formulas. We are getting the different amount of power required and also the power required by the pump operation. So therefore we can know in the last in petroleum storage and transmission neighborhood, it is necessary the greater the difference in height between the two tanks, means more power the power is used to lift the water against the gravity. So for the studies effort, this table is conducted for the justify the parametric analysis were carried out by altering the elevation difference while keeping all other operating setting constant. So therefore we are justified that is the more different elevation there is, there will be the more power is required by the pump to operate the crude oil from the storage tank to the pump tank.
Okay, good afternoon, doctor. My name is Kishan Guest from Chandran, number metric TH24039. So I'm going to present my part in this as a project, which is results and discussion about the evaluation difference delta Z and versus power required by pump. What? Okay. First of all, I want to show the diagram that our project and the relationship between the evaluation difference and the power that the pump needs to lift the crude oil from the low level collection tank to the elevated storage tank is shown in this figure. The result indicate a significant positive linear relationship between the power requirement and the evaluation difference. The pump power increases from about 25 watt at evaluation difference of 15 meter to about 55 watt at evaluation difference of 45 meter. This trend means that more energy input is needed if the crude oil is to be raised to higher elevations. The observed increase in power requirement can be explained by the principles of fluid mechanics and energy conservation. As the difference in elevation increases, the pump must work harder against gravity to raise the crude oil to a higher potential energy level. The chance the change of the gravitational potential energy of the fluid is proportional to the difference of elevations. Thus, the higher the vertical distance from the collection tank to the storage tank, the higher is the energy demand on the pump. Okay. Then the booster pump in this scenario is the main source of energy that allows crude oil to transfer from the lower collection tank to the upper storage tank. If the storage tank is at an elevation above the the pump will have to generate a higher pressure head to overcome the increased static head. As a result, the power consumption of the pump increases. This accounts for the linear trend seen in the result, where each increase in elevation difference corresponds to an increase in pump power. Also, the graph is linear, which means that other parameters such as flow rate, fluid properties, and pipeline conditions were kept constant during the calculation. Here, the power requirements is the mainly governed by the evolution differences. Then the result agree with the theoretical pump power equation in which the power is proportional to the total rate the pump must overcome. Okay. Uh,
Okay, hello everyone. My name is Suman Alakam Selbum. My metric number is TH24009. For the conclusion, we conclude this mini project successfully apply the work and energy principle to analyze the transportation of crude oil from a lower collection tank to the highest storage tank using booster pump. From our calculation, the minimum pump work required was found to be 157.65 joules per kg, while the pump power required under the given operation condition was approximately 15.81 kilowatt. Our results show that the elevation difference has the greatest influence on the energy requirement. Compared to the changes in kinetic energy, the increase in potential energy contribute much more to the total pump work. We also observe that as the elevation difference increase, the pump power increase linearly. This means that transporting crude oil to higher storage tank requires significantly more energy. Based on our mini project, we recommend selecting efficiency pump with appropriate power rating to improve performance and reducing operational costs. In addition, pipeline and storage system layout should be designed to minimize unnecessary elevation difference whenever possible. Future studies should also include factors such as friction loss and actual pump efficiency to obtain results that are closer to a real industrial condition. Overall, this project helped us understand how engineering dynamic can apply to real petroleum transportation system and highlighted the importance of proper pump selecting and energy efficiency system design. Thank you.